So what are we doing today? Well, we're going to differentiate between thermal, heat transfer, and fluids. I'm going to define the zero, first, and second law of thermo, just very basic. And then we're going to recognize open and closed systems. Okay. So we got some definitions that I kind of want to get through, some sketches. So it may take a little bit to do some of the sketches. All right, so let's look at, thermo. Thermo is red, right? Let's do red. So here's some definitions of each one. So we're going to look at thermo, heat transfer, and fluids. So thermo is this. Oh, I shouldn't have done that. Heat transfer is red. That's all right. And I'm going to write the three definitions and then we'll talk about each one. All right, so thermo is really the study of energy use and the transformation to one form into the other. Okay, so it's basically conservation of energy in a big scale. Heat transfer is really only the energy flow that's due with temperature differences. All right, so in this room it could be 50 and then outside it's maybe 20. So the temperature will go outward, okay? And the interaction between the wall, which we call conduction, and the interaction inside here and outside, which could be radiation and convection. Some of you have taken heat transfer. Anybody take heat transfer yet? Just one of you. Okay. All right. And you have two? Okay. So that's what it basically heat transfer is: conduction, convection, and radiation. And the sun is radiation too. The sun radiates in, it hits some of the desks, okay, it heats it up. That's what they call radiation. And then fluids is really the study of fluids, which is, again, what is a fluid? Liquid or gas. Fluid students just had that, yep. At rest or in motion, okay? So those are the three basic things. Now let's look at an air conditioner. We're going to draw this sketch and try to figure out why it's not moving. There we go. And kind of define each case. All right, so let's make this nice, pretty sketch. All right, so what I'm going to label some stuff. two more things. Let's do orange. So by the end of the class, end of the semester, you'll be able to draw this. This is one of your final, like if you pick air conditioner, you would draw this, label it, then do the analysis on each little case and determine what really the power of the motor or whatever you needed to get this to work at a certain flow rate, at a certain temperature that you want, okay? So this is like the big picture, and what we do is little bit pieces here and there until we work up to this. So here, basically, we have an electric motor on the right, and it's basically causing this compressor to spin and get this, what they call a refrigerant, to cycle through this system. All right, and we'll explain that, okay, these are different pipe sizes, you have different flow rates. Okay, if something's moving too fast, the heat exchange doesn't quite work. And you learn that in thermal, but also in heat transfer, you do that too. Okay, well, let's kind of start over here. This is a throttling valve. It basically is like a regular valve you can screw down that basically pinches, you want to think of the amount of size of the pipe. So it could be from here, then it pinches it down. When you pinch it down and the flow goes through it, it expands after. And when it expands, it cools. Okay, so the refrigerant's cold here. So it's cold through here, and it gets to this heat exchanger. And pretend this section right here is hot, hotter than this. What's going to happen? The hot air is going to go and absorb this and do what to the refrigerant now? It's going to heat up. Yeah, it could evaporate, but this doesn't. The refrigerant's kind of nice. It doesn't. But it heats up. What happens now to the room? It cools down, right? Because that heat energy now is being sucked into the refrigerant. Now the refrigerant's warm, and it goes back to the cycle here. So that actually kind of cools the room. It's kind of cool how that works. So it goes through here, it's cold, then this heat exchanger takes this hot energy and warms up the refrigerant. Now it's hot refrigerant here, okay, and then it goes back through the whole cycle. Does that make sense? So now let's look at, okay, what's the thermal, what do we do for thermal analysis, heat transfer analysis, and fluids for this particular thing, okay? So let's do blue here. So thermo. What does the thermo analysis tell us? Well, it's kind of what I said initially. Would tell us how much electric power is needed. To obtain a desired amount of cooling. Let's visualize this for a second. You have your power cord from the electric motor and you plug it into the wall. Okay, that has a power now, right? It has an amount of current and it has voltage that gives you power. That runs to the electric motor. Inside the electric motor, what's happening? That electric energy is being converted to motion or shaft, right? But what happens when things are moving? They create friction, right? So you have efficiencies. And we'll talk about those here in the next week or two. There's an efficiency of the electric motor. So coming from here, through here to this, you're going to lose energy, right? So whatever's coming in should be higher than what's going out. Okay, that's why we have efficiencies. Then it goes into the compressor, and then the compressor is now spinning too. So you lose some energy from that, because you have some friction losses. And then it goes around the whole circle. So depending on how much input we put here determines really how fast this flow is going around, right? And it really reacts is how much energy can from here go into there. So that's what thermal will tell us. And we'll do plenty of that, trust me. All right, so what does heat transfer tell us? Anybody want to guess? And what sections of that am I looking at? Yep. The ones that are in red, which are the heat exchangers. So it basically, how big to build the heat exchangers? Yep. And if you really want to see heat exchangers, we have a couple in the lab. Actually, one now. The other one left. I don't know where it went. And fluids. I'll do black. That would actually tell us how big the pipes must be. Because if you remember, some students that have taken fluids, when you start getting flow in a pipe, that depends on a whole bunch of stuff, right? Yep, it would, yes, yep. So basically, when flow is going through a pipe, there's friction, and you need to overcome that friction. It depends on the size of the duct, of the pipe. So we're really primarily going to focus on the thermal analysis, but you still need to know some of these other concepts, because if you notice, they all are together in one, right? All right, so let's look at this. So that was kind of objective one. Let's do the zero first and second law. And I think we might have some time to actually start the homework, so that'd be good, right? You can thank me later. All right, so thermo and energy. And let's draw this little sketch here. They're supposed to be all the same size. I should buy a ruler, a nice ruler that I can put on here. Oh, I could make boxes, but that's all right. Oh, sorry, this is the zeroth law. So the zeroth law is actually very straightforward. If you have 3 people or more people touching, it doesn't really matter. If 2 of them are, eventually, if 2 are in equilibrium and the other 2 are in equilibrium, then obviously the 2 that are last have to be in equilibrium, okay? So think of this, if 3 people are touching hands, and eventually all 3 will be in equilibrium. That's what the zeroth law basically states, okay? And that's what we'll do. Anytime you get to a state, it reaches that temperature and it's in equilibrium at that certain state, at that certain temperature, okay? Yeah, that's what we're going to assume. It's kind of okay, steady state. Now, when we get to open system, steady state kind of means slightly something different, but we'll get to that. Okay, so that's the zeroth. Let's do the first law. I think everyone's had physics, right? Okay. So, you remember what physics stated? That let's just do conservation of energy. We'll expand on it. Whoa, I didn't mean to do that. Where's the undo? And we're going to add internal and other things, but Basically, the first law is the conservation of energy. That means that two states, they're the same. So we can think about it as here's a person, and here's a person. They're rolling down the hill. Sure. Two different states. At state 1, what does he have? Yeah, potential energy. Bless you. Or whatever that was. I'm not sure. Was it a sneeze or a nose blow? So state 1 is all potential, and then it converts at state 2 to all kinetic. Okay? That's the basic fundamentals of this. It's going to be important when we start dealing with this is to draw this red line over here. It's called a datum. Okay? Anything above the datum has positive potential. Anything below has negative. Okay? So when we get to that, signs are going to be tricky. So always remember that. Okay, and the second law, I'll do red, that's fine. You remember what I told you on the first day what the second law was about? Entropy, yeah, wow. Yeah. Basically, that means it tells the direction of heat transfer or heat flow. Let's look at closed and an open system. Okay, because these are going to be key. And you're going to have to identify and draw stuff in the future homeworks. So let's do a closed system first. Learn to make robots. Sweet. This is a cylinder, a piston cylinder, and which is the black outside. And then I drew a boundary, which is an imaginary dotted line, kind of almost touching the outside walls. So that dotted boundary contains all the air inside, if it was air or any type of liquid or gas, okay? So when we start getting to closed, I think it's chapter 3, your sketches should have a boundary, okay? Because what can cross the boundary? Heat, which is Q, okay? So heat can cross the boundary. What can also happen, the piston can move up and down, right? And that piston, when it moves up and down, is what we call work, all right? We could also stick a sealed paddle wheel in here, and you have shaft work coming in, and we'll talk about that later. But the piston can move up and down, so that's work. If it's a closed system, it's sealed off, so the mass of the air always remains constant as we expand it. Okay? Mass is always conserved in this case. So what does that mean? Well, if you expand it, the volume increases, right? and the mass stays the same. So what happens to the density? Well, what's the equation for density? Mass over volume. So if the mass is constant and the volume gets bigger, then it should get smaller, right? Because if the volume gets smaller, the number on the denominator gets smaller, and therefore the density goes up. Okay? That's the way I look at it. Good. Does that make sense? So there's no mass crossing the boundary. It can't. Physically cannot. All right, and then an open system is kind of, I mean, I think you got it now. I'm just going to flip the cylinder around. Don't ask me why I did it. It doesn't matter. And now there's little valves, intake valves and outtake valves. Oh, let me put, we might as well put energy and mass across boundary. So you can have energy, you can have heat, you can have the piston move up and down, and you can have some sort of mass come in or mass go out. It all depends.